Welcome to the 6.4 lesson video. Today we're going to be learning about rational exponents. Our objective is that we can simplify expressions with rational exponents. So let's begin by talking about how we can write a radical expression in an equivalent form using a fractional or rational exponent instead of a radical sign. So in general, the nth root of x can be written as x to the 1 over n power. So the n, the index, that number goes underneath, and then the exponent next to the radicand, x to the first, that 1 goes on top of that rational exponent. And that's for any positive integer n. So here's a couple examples to make this make a little bit more sense. So if we were taking the square root of 36, we know by now that if there is not an index in front, we know it's a 2. And also, if there is no exponent next to the 36 or whatever numbers in the base or the radicand, we know that's an invisible 1. So I can write this as 36 to the 1/2 power. So whenever you see a 1/2 in the exponent, you know that that is a square root that we're working with. Similarly, in the next example, we have the cube root of 64. Well, the index is 3, as indicated, and the exponent, 64, is being raised to the first power because there's no other exponent there. So we can write this as 64 to the 1/3 power. So when you see 1/3 in the exponent, that means we're working with a cube root. Here's one more example. The 4th root of 16, well, the index is 4, and the exponent next to the 16 is an invisible 1. So we can write this as 16 to the 1/4. So when you see a 1/4 in the exponent, that means we're working with the 4th root. So now let's take a look at example 1 and learn how to simplify each of these expressions using rational exponents. Before we begin part A, take a look at this little think box at the left. It says, what does the denominator of the fractional exponent represent? Well, the denominator of that exponent is the index of the radical, as we just talked about. So the denominator of the 1/2 is 2, and that was a square root, so the index is 2, etc. So in part A, we're given 216 to the 1/3 power. So that means I can rewrite this as the cube root of 216. Now we do essentially have a little 1 in the exponent, but remember that doesn't really do anything. So you can choose to put that there or not. And then we can rewrite 216 as 6 cubed, because 216 is a perfect cube. So now if we're taking the cube root of something cubed, we just get the number in the base. We talked about this in previous lesson videos. So we're just going to get 6. So that means 216 to the 1/3 power is equal to the cube root of 216, which is equal to 6. In part B, we have 7 to the 1/2 power times 7 to the 1/2 power. There's two ways to solve this problem, so I'd like to show you both. Let's use the radical approach first. So remember, if something's raised to the 1/2 power, we're essentially just taking the square root of that. So square root of 7 times square root of 7. We can multiply these because we have the same index. It's a square root. So that means we have square root of 7 times 7, which is equal to square root of 49. And we know that square root of 49 is equal to 7. So 7 to the 1/2 power times itself is just equal to 7. Another way to do this is just by keeping the rational exponents involved. We learned this in Algebra 1, that if we're multiplying two bases that are the same, we can just add the exponents. So when we add 1/2 plus 1/2, we just get 1. So that means we have 7 to the first power, which is equal to 7. So we get the same result using a separate method. In part C, we have 5 to the 1/4 power times 125 to the 1/4 power. Because these are both being raised to the 1/4 power, I know I can rewrite this as radicals with an index of 4 in front. So I'm going to write the 4th root of 5 times the 4th root of 125. Because these have the same index, I can use a property for multiplying radical expressions and multiply them together under one radical. So the 4th root of 5 times 125. 5 times 125 is 625, so I can rewrite this as the 4th root of 625. And since we're taking the 4th root, I want to see if there's any number that I could raise to the 4th power to get 625. And we actually can rewrite this as the 4th root of 5 to the 4th. Remember, when we're taking a root, the index and the exponent, if those match, that means they're undoing each other, so we really just get 5 for our final answer. So 5 is the simplified form of the original expression. For all of these problems, you can always use your calculator to check your final answer just by raising the original expression to the indicated exponent. Before we generalize this idea for any value in the exponent, I'd like to discuss one example that proves the advantage of changing radicals to exponential expressions, and that's shown right here. The cube root of x times the sixth root of x. So if we just kept it in radical form, we wouldn't be able to combine this because they do not have the same index in front. But if we were to change this to exponential form, we would have x to the 1/3 times x to the 1/6. These do have the same bases, so that means if we're multiplying the same base, we can add the exponents. So that means we have x to the 1/3 plus 1/6. In order to add those fractions, we do need to have the same denominator, so I can change 1/3 into 2/6. That's the equivalent form with the same denominator. So I have 2/6 plus 1/6, that's equal to 3/6. And then reducing that, it gives me x to the 1/2, and we know by now that x to the 1/2 is the same thing as the square root of x. So you can see that by changing the radicals into exponential form, it helped us in simplifying the original expressions. So far, we've only been working with rational exponents that have a 1 in the numerator. That's not always the case, so now we are about to generalize this idea for all rational exponents. So let's focus our attention on the key concept box. If the nth root of a is a real number, m is an integer, and m over n is in lowest term, aka simplified as much as possible, then we can write a to the 1 over n power as the nth root of a, which we already talked about. This is the new part right here. A to the m over n power is equal to the nth root of a to the m power, which can also be written as the expression the nth root of a raised to the m power. So what that is saying is that you can either put the exponent right next to the a, so a to the m power, or you can raise the whole nth root to the m power. And you need to realize that if m is a negative number, a negative exponent, then we do not want to have a as 0, because then we would have to be working with 0 in the denominator, which we do not want to do. Example 2 is going to give us the opportunity to convert between exponential and radical forms, and hopefully we'll get more comfortable with these processes. So in part A, we have x to the 3/7 and y to the negative 3.5 power. We need to change each of these into radical form, and that will be separately. So let's focus on x to the 3/7 power first. And whenever you're given a fraction, you want to make sure that's as simplified as possible. We cannot simplify 3 over 7. It's already in lowest terms. So now I can write this as the 7th root of x to the 3rd. Remember, the bottom of the fraction always is the index, and then the top of the fraction can either go underneath the radical with the x, or we can write this as the 7th root of x all raised to the 3rd power or cubed. Now we're going to change y to the negative 3.5 power to radical form. So first thing I'd like to do is change this into fraction form or rational exponent form. And I know that negative 7/2 is equal to negative 3.5. Hopefully you remember from Algebra 1 that when you have a negative exponent, you want to take that term and put it in the denominator. We're essentially taking the reciprocal. So 1 over y to the 7/2 power. So that takes care of that negative in the exponent. From there, I'm going to rewrite this as 1 over the square root of y to the 7th. Remember that 2 is the index, so we do have a square root there. From there, we can simplify further. So I'm going to break apart y to the 7th. The biggest exponent that I can take the square root of is y to the 6th, because that's an even number, so we have a leftover y. And when I take the square root of y to the 6th, I get y to the 3rd. And then I still have square root of y in the denominator. So now I have 1 over y to the 3rd times square root of y. Remember from previous lesson videos in this chapter that we do not want to stop there. We don't want to have a radical in their answer. So I'm going to drop that down. And in order to take care of that issue, we need to multiply by the radical itself. So square root of y over itself. So we are essentially multiplying by 1. So that means I have square root of y in the top. The y to the third is still there, and when I multiply square root of y times itself, I just get y, so y to the first essentially. And simplifying that a little bit more, I can write this as square root of y over y to the fourth. So the original form, y to the negative 3.5 power, is equal to the square root of y divided by y to the fourth. In part B, we need to change each of these radical expressions into exponential form. So the first thing I have is square root of a to the fifth. So I know that a square root has an index of 2, so I'm just going to put that there. And I can rewrite this as a to the 5/2 power. Remember, the index is the denominator of the fractional exponent, and the exponent a to the fifth, that 5 goes on top. So a to the 5/2 power. Now let's simplify or put the fifth root of b cubed into exponential form. So I know that the fifth root of b can be written as b to the 1/5 power, and it's still cubed. And then we remember from exponent rules that we can multiply those powers. When you're raising a power to a power, you just multiply them. So that means we get b to the 3/5 power. So that would be the exponential form of the original radical. Example 3 gives us the opportunity to apply our knowledge of rational exponents. So let's read this together. Kepler's third law of orbital motion shows how you can approximate the period p in Earth years it takes a planet to complete one orbit of the Sun. Use the function p is equal to d raised to the 3/2 power, where d is the distance from the planet to the Sun in astronomical units, AU for short, which is approximately 93 million miles, or the distance from the Earth to the Sun. How many Earth years does it take Mars to orbit the Sun? So what we're going to do is use the formula that's provided. P is equal to d to the 3/2 power. In the picture, you can see that the distance from the Sun to Mars is approximately 1.5 AU. So because D is measured in AU, or astronomical units, we're going to be plugging in D. We're going to be plugging in 1.52 for D. So 1.52 raised to the 3/2 power. Now we're going to use the calculator to assist us in finding this approximate distance. So let's type in 1.52 and then caret for the exponent button and then 3/2. Enter. So rounding to 2 decimal places, that means we get 1.87 approximately. Now I'd like to show you how to use the square root feature to do the same thing. So raised to the 3/2 power just means you are taking the square root of 1.52 and then cubing it after that. So let's take the square root of 1.52 and then raise it to the 3rd power, or cube it. And you can see that we get the exact same value. So that means it takes Mars approximately 1.87 Earth years to orbit the Sun. So as the distance from the Sun increases, so does the period. So it takes longer for the planets to orbit the Sun the further out they are from the Sun. So now let's take a minute to go over all the properties of integer exponents, because these apply to rational exponents. So we're going to let m and n represent rational numbers, and we're going to assume that there's no denominator that is equal to 0. Focus in on the first property that's given to us, a to the m times a to the n. Remember, when we have the same bases that are being multiplied, we can add the exponents, so we get a to the m plus n. So let's look at the example here. 8 to the 1/3 times 8 to the 2/3. They have the same base, which is 8, so we can add the exponent. So 8 to the 1/3 plus 2/3, that is equal to 1, so 8 to the 1st power is equal to 8. The second property, we are taking a power and raising it to another power. So when we have a to the m power raised to the n power, we can multiply those exponents and we get a to the m times n power. So making that a little bit more applicable, we have this example, 5 to the 1/2 power raised to the 4th power, so we can multiply those exponents. So we have 5 to the 1/2 power times 4. 1/2 times 4 is 2, so that means we get 5 to the 2nd power, which is equal to 25. Right below that, we have the product of a times b raised to the m power. We can share that exponent and simplify and have a to the m times b to the m power. And then an example of this would be 4 times 5 raised to the 1/2 power. We can share that exponent, so we have 4 to the 1/2 times 5 to the 1/2. 4 to the 1/2 is just the square root of 4, which is equal to 2. And then 5 to the 1/2 cannot be simplified, so we have 2 times 5 to the 1/2 power. 3 more properties shown at right. When we have a negative exponent, we can take the reciprocal of that expression and take care of that negative exponent. So a to the negative m power is equal to 1 over a to the m power. An example of this would be 9 to the negative 1/2. We can rewrite this as 1 over 9 to the positive 1/2. 9 to the 1/2 is the square root of 9, which is equal to 3. So that means the simplified form would be 1/3. In the middle, we have a to the m power over a to the n power. When we are dividing the same bases, we subtract the exponents. So this property is the opposite of the first property that we talked about right over here in the top left-hand corner. So when we have a to the m over a to the n, we can just write a to the m minus n. Here's an example. 7 to the 3/2 power divided by 7 to the 1/2 power. Subtracting those exponents, we get 7 to the 3/2 minus 1/2 power, which is equal to 1. So 7 to the first power is equal to 7. Here's the last property, and this is actually really similar to the one directly next to it on the left side, except division this time. So if we have a fraction a over b raised to the m power, we can share that exponent, so we have a to the m over b to the m. An example of this would be 5 over 27 raised to the 1/3 power. That is equal to 5 to the 1/3 power over 27 to the 1/3 power. The top stays the same, 5 to the 1/3 power, and the bottom, 27 to the 1/3 power, is equal to the cube root of 27, which is equal to 3. So that means the simplified form would be 5 to the 1/3 power over 3. We're going to be using these properties of rational exponents in the remainder of this lesson video. So if you haven't written these down yet, I suggest doing that now. Recall from section 6.2 that when we were simplifying products or quotients involving radical expressions that had different indexes, we were not able to do so. However, we can combine radical expressions with different indexes if we convert them into rational exponent form. And that's what we're about to do in example 4. We are given the 4th root of x to the 3rd divided by the 8th root of x to the 2nd. The radicands are different, but both are powers of the same variable. So we're going to write the expressions using exponents. So I can write the top or the numerator as x to the 3/4, and I can write the denominator as x to the 2/8. Now what I want to do, since this is division, I can use the division property for exponents and subtract the exponents. So I can write this as x to the 3/4 minus 2/8. Remember, when you're adding or subtracting fractions, you definitely want to have the same denominator. If we were to reduce 2/8, we would get 1/4. So we have x to the 3/4 minus 1/4. That is equal to x to the 1/2. And we know that when we raise something to the 1/2 power, we're essentially taking the square root. So the simplified form of the original radical expression is the square root of x. When we are asked to simplify a number with a rational exponent involved, there's 2 different methods we can choose from. The first method is where we would just use the properties of exponents to simplify. The second method is when we need to convert to a radical expression and then simplify. I'm going to show you both methods for the next example. In example 5, part A, we need to simplify 16 to the negative 2.5 power. The first step is to rewrite the decimal exponent as a fraction in lowest terms. So I can rewrite this as 16 to the negative 5/2 power. I know that 16 is equal to 2 to the 4th, so I'm going to rewrite this as 2 to the 4th raised to the negative 5/2 power. Because I'm raising a power to another power, I can multiply these numbers. So 2 to the 4th times negative 5/2. That is equal to 2 to the negative 10. We can rewrite that as 1 over 2 to the positive 10 power, and 2 to the positive 10 is equal to 1024, so that means 16 to the negative 2.5 power is equal to 1 over 1024. So the first method that we just used was using the properties of exponents. Now in the method 2, we're going to be changing this into radical form. The beginning is still the same. So we're still writing this as a fraction in lowest terms. And because we have a negative exponent, I'm going to write this as 1 over 16 to the positive 5/2 power. From there, I can change this denominator into the square root of 16 and then raise that to the 5th power. So 1 over the square root of 16, because the denominator was 2, so that means I'm taking the square root and raise that to the 5th power, because that's the top of that fractional exponent. The square root of 16 is equal to 4, so I have 1 over 4 to the 5th power, and 4 to the 5th power is equal to 1024. So I still get the same answer using both methods. In part B, we need to use both methods to simplify negative 32 to the 4/5 power. The first thing I like to do is rewrite negative 32 as negative 2 raised to the 5th power. That is equal to negative 32, and we still have the exponent 4/5. Because I am raising a power to another power, I can multiply those exponents. So get negative 2 raised to the 5 times 4/5 power. When I multiply 5 and 4/5, I just get the numerator 4 because the 5's cancel out. So I get negative 2 raised to the 4th power, which is equal to 16. So that means negative 32 raised to the 4/5 power is equal to 16. Now in method 2, I'm going to change this rational exponent to a radical. So I'm going to rewrite this as the 5th root of negative 32 and raise that to the 4th power. Remember, the bottom of the fraction is the index and the top of the fraction is the exponent outside. So I'm going to rewrite this as negative 2 to the 5th power, similarly to method 1. We're still raising it to the 4th power. When we take the same root as the exponent, remember those cancel out, so we just get the number underneath. So we get negative 2, and we're raising it to the 4th power, and we get positive 16 again. In our last example, we are given a couple expressions where we need to write them in simplest form. What's the first step in simplifying a radical expression using the properties of exponents? We want to write the radicals using rational exponents. So I'm going to write this as negative 8 raised to the 2/3 power. So I'm sharing the exponent 2/3 with each of the terms inside. And I'm going to write times x to the 2/3. The next part, the square root of xy, can be written as xy to the 1/2 power, and we're raising that to the 2/3 power as well. I can rewrite negative 8 as negative 2 to the 3rd power and raise that to the 2/3 power. Drop down x to the 2/3. And then now I'm going to be multiplying these exponent because I'm raising one power to another power. So that means I get xy to the 1/3 power. Simplifying this further, the first term, the 3 and the 2/3 are being multiplied. When you multiply, those 3's are canceling because there's one on top, one on bottom. So I just get negative 2 to the 2nd. Drop down the x to the 2/3. And the last term, I'm going to be sharing the 1/3 with the x and the y. So x to the 1/3, y to the 1/3. From there, I'm going to combine like terms, and I get my final answer of 4x y to the 1/3. These x terms right here, I can add the exponents because they have the same base, and I just get positive 1. So I get 4xy to the 1/3. We could also write this as 4x times the cube root of y. In part B, we are given 16y to the negative 8th power raised to the negative 3/4 power. So first thing I do is I share that negative 3/4 with each of the terms inside the parentheses. So I get 16 to the negative 3/4 power times y to the negative 8th power times negative 3/4. I'm going to simplify this further by rewriting 16 as 2 to the 4th, and that's being raised to the negative 3/4 power. And then multiplying these exponents here, I get y to the 6th. When I'm multiplying the 4 and the negative 3/4, the 4's cancel, so I just get 2 to the negative 3rd times y to the 6th. 2 to the negative 3rd is 1/8 times y to the 6th is just y to the 6th over 8. So that would be the simplified form of the original rational exponent expression. Thanks so much for sticking with me. If you're listening right now, if you could just write on the side, I made it. I would very much appreciate to know who is listening and following along with my lessons. Now we just have our lesson check below, so take a moment to write down all 6 problems, work through them, and let me know if you have any questions the next time we meet.